Hello, so in this video we're going to start this topic by looking at gradients of curves, okay? So this is basically going to be like a GCSE recap and nothing really new here, but it will be an important building block for this topic later on, okay? And in the next section we will be using the ideas that we see in this video here. So yes, it's nothing, it's still important, but let's have a look then. So gradients of curves then. So as a reminder, the gradient of, let's say, a line, right? Let's say this line here. The gradient represents how steep a line or something is. So for example, imagine you have a person here, and then imagine this is some sort of hill or something they're climbing on. So the gradient is basically the steepness, right? Steepness of a line or curve, okay? Okay, and now let's consider this example then. Let's say we have a line up here. Now imagine that now we're still climbing up the line, right? Imagine the line is some sort of hill or mountain. It's going to be a lot harder to climb up it, right? So the steepness is higher. So the gradient is going to be higher in this second example than this one, right? And now imagine, let's say, it's downwards instead, and now imagine we're basically at this point it's kind of like going down a slide, so there's no real steepness at all, right? It'd be a negative, right? Negative steepness, as we're not really going up anymore, we're going down, okay? So we have a negative gradient if the line is going down, okay? And then lastly, there's no gradient if it's just completely flat, right? So completely flat surface, so the gradient is equal to 0 here. In this example here with the slide, almost, the gradient is negative because it's going down. Here the gradient is positive, but it's very high, very steep. And here the gradient is still positive, but it's lower than this second example here. So we've got positive gradient here, a more positive gradient, a negative gradient, and it's going down, and then no gradient because it's completely flat, okay? So we've seen this should be a recap when we looked at straight lines, right? And we can also do that with curves as well, right? The exact same idea. So if we then let's say we have a quadratic curve like this, well then let's say we have a point here. Well, obviously the steepness of the curve changes throughout the curve, right? So then what we want to do is, at a particular point, we can find the gradient by drawing a tangent to the curve, to the point, which would look something like this, right? Okay, something roughly like that, okay? So the gradient is a curve where it touches the point to the curve, right? And so then if we calculate the gradient of the line of the curve, this tangent, then if we calculate the gradient of the tangent, that gives us the gradient for the curve at that point, okay? So I'm going to say the tangent to a curve at a point tells us the gradient of the curve at that same point. And so that's the whole idea with this sort of section, right? This whole section basically is to do with gradients, right? And how basically the tangent at a point on the curve, we can draw a tangent towards that point on the curve and then calculate the gradient to tell us the gradient, right? And so that's the whole that's the whole idea here. You would have seen this at GCSE. You would have drawn tangent lines towards a point on the curve to estimate the gradient of the curve at that point, okay? So we're going to look at some examples then. So we've got this example here. We are told this diagram shows the curve with equation y is equal to x squared, right? The tangent t, which is this red line here, right? The tangent t, if you can see it, that red line there, to the curve at the point A11, so A is there, point 11, is shown. Point A is joined to the point P by the chord AP. So P is here, A is here. The chord is the blue line here. Okay. Actually, let me zoom in. Actually, probably very helpful to zoom in. Okay, let's see how that goes. Okay, so hopefully you can see more clearly that then we have this blue line, this line from A to P, that's a chord, right? So firstly, we need to calculate the gradient of the tangent. So the tangent again is the red line here. So again, think back to GCSE or in chapter 5 when we looked at straight lines. The gradient of a line is simply changing y over changing x. So in this case, for the red line, the tangent here, the tangent t, this line t here, we need 2 points on the curve to calculate the gradient. Well, we've got 1 point already, A at 1, 1, okay? But we need another point on the line to then compute the gradient of it, right? So this is where we're going to need to use the graph. I might need to zoom in a bit more, actually, I'm not sure. But I noticed I can use this point here. Let's look for a nice point, right? So I notice here, when x is 3, if I then read off, hopefully you can see, I'll zoom in a bit more, but we get to y is 5, okay? So we've got this other point on the curve by using the graph, okay? This point is x is 3, y is 5. Okay, so therefore we can then compute the gradient between these 2 points by doing changing y, changing x, which I just done, right? If I do that then, well, changing y, let me note my 2 points here, 1, 1 and 3, 5. So then if I do changing y between these 2 points, well, at this point here, y is 5. Take away the y here at 1. Then we do the same for x. So changing x is 3 here. Take away 1 there. Okay. If we do this calculation, we get 4 over 2, which is 2. That tells me then that the gradient of the tangent is 2 of that red line. Right. The gradient of this red line t is 2. And more particularly, because the tangent is the tangent at the point A on the curve, that tells me at the point A on the curve x squared, the tangent is 2. Okay, so the steepness of the curve at that particular point A is 2. Right, now for part B, for part B we need to calculate the gradient of the chord AP. So again, now this blue line where P has coordinates, firstly 1, 2, 2, 4, sorry. Well, we don't actually need the graph really at this point, because to calculate the gradient from A to P, the gradient of the chord AP, we just need to take the point A. So I'm going to say A is blah blah blah. What was A? 1, 1. Yeah, A was 1, 1. And we're also then given the point P is equal to, firstly, 2, 4. So if we were to compute the gradient of the line between A and P, these 2 points, we can then use the changing y and changing x formula, okay? So therefore the gradient then here is going to be changing y. So let's take P, right? So 4 here, take away 1, so ya. And then we do changing x, right? So 2 at P, take away 1 at A. If we do that, we get 3 over 2, okay? 3 over 1, sorry, so that would just be 3, okay? A gradient of 3 there. Now we're told, in the second part, now P P has to be 1.5 and 2.25, okay? So now we're basically, what we're doing is we're essentially moving P about, right? We're moving P, so we're starting here at P, which is at 2, and now we're moving it to 1.5, okay? So that P would be about there somewhere, right? So now in that case, well, we don't need to use the graph to find the gradient, because we can just use the points we've got. So if we calculate the gradient between A and P, in this example, well, the gradient's going to be changing y, changing x. So y at P is 2.25, take away 1 from A, then 1.5 for x, take away 1. If we do that, we get 1.25 over 0.5, which would be 5 over 2, or 2.5, okay? There we are, okay? Now in this example here, in the third example here, we now have P's 1.1 and 1.21, okay? So again, P is starting to move closer to A. So now 1.1 will be about there on the curve. So hopefully you can see we started with P at 2 here, then P at 1.5 for x. Now P is 1.1 for x. So we're getting very closer, very much closer to A. Okay. So now 1.1. So then the gradient now between A and P, well, x is 1.1. No, sorry, changing y. So y is 1.21. Take away 1 over changing x, which would be 1.1 minus 1, and then if we do that we get 2.1. Okay, cool. And hopefully you also start to notice some sort of pattern of what's happening to my gradient in relation to part A. Hopefully you notice what's happening there with my gradients. Okay, now for the fourth part, we now have P to be, what was it? P is now 1.01 and oh god, and then 1.0201. Okay, so let me copy that down. P is 1.01, what is it? 0201. Yes, okay. So therefore the gradient in this case between A and P is going to be 1 point changing y, so 1.0201 minus 1 over 1.01, take away 1, which will get me, if I put that in the calculator, 2.01. So hopefully you notice the pattern you're spotting is getting warmer, right? Okay, then for part 5, we now have P is now this 1 plus h, and 1 plus h squared, okay? So there's a bit of algebra, but again, 1 plus h all squared, but again, h is just a letter, it's just a number, right? So we can do the same thing as if it's just a number. So therefore the gradient in this case, right, well, it's changing y, but obviously we've got 1 plus h squared, so it's going to be 1 plus h all squared for the y at P, and then take away the y at A, which is 1. Right, take away 1, then we do change in x. So at x then, for P it's 1 plus h, take away 1 at A, right? If we simplify it, well, that would be h plus 1 squared minus 1, and then we can simplify the bottom bit, because 1 plus h minus 1, well, 1 minus 1 is 0, so it's just over h. Right, so then we can perhaps expand this bracket on the top here, so let's see if any of it simplifies. If we do that then, well, h plus 1 squared, remember, is h plus 1 times h plus 1 times by itself. Then we can expand it in how we normally expand brackets. So that'd be h squared add h would be 2h add 1. So if we then substitute that in, we get h squared add 2h add 1 minus 1 over h, right? There we are. But again then, notice now we can simplify the top, because 1 plus 1 minus 1, 1 minus 1 gets me 0, so it's just h squared add 2h over h. Right, but I can actually cancel both sides by the top and bottom by h. If I factor a h out on the top, h of h plus 2 over h, right? It's like simplifying algebraic fractions, right? We then get h plus 2 as my answer. So that would be, the in terms of h then, that would be my simplified gradient from a to p with this coordinate p here. Right, okay, yeah, and hopefully you notice what's going on. So again, a p is again moving even closer to a. So what was it, 1.1? Then 1.01 would probably be about there, and then remove it. It's basically at a, pretty much, right, as we get closer and closer. Right, so part C then, comment on the relationship between my answers to part A and B. So hopefully that's basically saying, have you noticed what's going on with the gradients I've worked out and my gradient in part A? So my gradient of my tangent to A is 2. So the gradient, and so what that means is the gradient of the gradient of the curve at A has to be 2, because that's my gradient of the tangent, right? What's happening then is, obviously when p is far away from A, then so again p was originally up here and A is down here. Well, I've got a gradient of 3, but then as we moved p closer towards A on my graph, well, what's happening? My gradients are getting closer and closer to 2. So actually that's saying then, as p gets closer to A, as I move p in this way towards A, then the gradient between A and P, if I draw the line, is basically matching the tangent, essentially, because the gradients are starting to equal. Right, so that is my relationship then. So my relationship would be part C. As P gets closer to A, point A, the tangent of AB, right, is the same as the tangent, is the same, oh no, the gradient of AB, sorry, is the same as the gradient, or getting closer to, is closer to the gradient of the tangent at A. And so that's what's going on. Right, okay, so that's my answer then. But then lastly, I want to talk about this H business. We will look at this in more detail in the next section. But this H then, hopefully you notice, well, 1 plus H then, so remember 1 plus H, the H is basically telling me how far away from A I need to be. So let's go back to my curve. P, at this point, P is 2, 4. So if A is at 1, 1, I'm 1 extra away from A, right? Because 1, 1 for A, so X is, so at A, X is 1, right? At this point here, P is 2, 4, X is 2. So I'm going from X is 1 to X is 2. So that means I need an extra 1. Right? So that means when I'm adding this extra number H here, so A is at 1, then I'm adding some more, right, to it to get to P. So in part 1, H would be 1. In part 2, I'm now gone to 1.5, so P has moved to 1.5 here. So now H is only 0.5, okay? So as I'm going from starting at 1, right, and then I'm adding an extra amount, that extra amount now would be from 1 to 1.5 would be 0.5, Okay, in this third example, h would then be 0.1. So again, you're starting to notice my h is getting smaller, which is basically the distance from A to P, right? It's getting smaller and smaller. The gap between them is closing. And so that h basically is the gap between A and P. And then here, in this fourth one, h is 0.01, so it's getting even smaller. And so what's happening is, h is shrinking towards 0, to where A is basically, well, or P is basically reached A, right? When that happens then, the gradient from A to P is basically matching the gradient of the tangent. And that makes sense then, because when h is 0 effectively, that goes away to 0, so I'm left with a gradient of 2, which is exactly the gradient of the tangent the gradient of the tangent I got in part A. So the gradient should be 2, right? Because that's what I worked out in part A. That's what the tangent gradient was. And that's what happens when A and P are just basically, they're not apart from each other. They're at the same point. So, or extremely close to each other. When they're extremely close to each other, when h is basically near 0, the tangent I get is, the gradient I get is basically 2 as well. So that's the whole idea. We will be looking at that in more detail next section. The whole idea is, as we move the point P towards my point I want A, the gradient then will basically match the tangent. Okay, right, let's have a look at another example then. Right, I'm gonna get back to normal size. There we are. Okay, so we've got this exercise question. So we've got the point G, which has coordinate 416, right? And it's on the same curve x squared. That we so then we need to find the gradient of the chords joining the point G to the points with coordinates. I'm going to say the point P, right? So P, firstly, be 5 and 25. So again, we're going to do this. We're going to do the same sort of exercise. So it's basically asking what's the gradient between the point G, which is this, and these points here. So when P, the other point, is 525. If we do that, then the gradient then is changing y, changing x between P and G. So that'd be 25 take away 16 for changing y. Changing x would be 5 take away 4. Well, 25 take away 16 is 9. 5 minus 4 is 1. So the gradient is 9 in this case. Then for part 2, they're asking now P, the other point is now 4.5 and 20.225. So the gradient between this point and G now is going to be changing y, changing x, which would be 20.25 take away 16 over 4.5 take away 4 for changing x. If we do that, we get 8.5. Okay, for the first part, P is now 4.1, 16.81, and again, hopefully you notice it's the same pattern, it's the same sort of question again. I'm starting at 5 for x, but now I'm shrinking to 4.5, 4.1, and the next bit's going to be 4.01. You notice it started to go to 4, so G is at 4 for x, so I'm starting to shrink. I'm making P close, this point closer to the point G to get a more accurate gradient of the tangent, right, at the gradient of the curve at G, right? That's the whole idea. I'm shrinking the gap between this G, this point G, and another point. Okay, so, and this point is on the curve as well, by the way. These points are on the curve x squared, right? If you substituted, say, 4.1 for x into x squared, you should get 16.81, right? So yeah, so the whole idea is, from 2 points on the curve, I'm basically making these 2 points closer and closer to each other to get an accurate estimate, or get accurate answer for the gradient of the curve at that point, so at the point G. Anyway, so let's continue with this. So the gradient here, so changing y will be 16.81, take away 16 over 4.1, take away 4, that would be 8.1. So if I do the same for the fourth point then here, so now P is now 4.01, 16.0801. So the gradient between G and P in this case is going to be 16.0801, take away 16 over 4.01, take away 4. If I do that, I get 8.01. So again, notice what's happening to the curve, to the gradient, sorry. Each time it's starting to go towards a certain value, right? I'm starting at 9 and 8.5, 8.1, 8.01. Very similar to the last example as well. So then lastly, I now have the point. I have the point 4 plus h squared. So again, h, we have some algebra, but nothing to be concerned about. So we now have 4 plus h for x, and then 4 plus h all squared for y. So then we do the same. So therefore the gradient between this point P and G, so that's y of 4 plus h all squared. Take away 4, because that's the y value at G. Then changing x is going to be 4 plus h for x here. Take away 4 from G. So then again we can simplify some stuff. So it's going to be h plus 4 all squared, take away 4. Then we can simplify the bottom, right? Because 4 minus 4 cancels out and I'm just left with h. Right. And then I can expand the bracket. If I expand h plus 4 squared, I'll get h squared, add 4h, add 4h, be 8h. 4 squared is 16, take away 4 over... sorry. No, y is 16 for G, my apologies. So it should be take away 16 here, my apologies. 16... then be taken away as 16, all divided by h. Okay, if I do that, then well h, so then again the 16, the plus 16 and the minus 16 will cancel each other out, so I'm left with h squared add h squared add 8h, h sounds everywhere over h. Alright, okay, now we can factorise the h on the top. And then we can cancel it, right? So then I'm left with 8 add h there. So that's my simplified gradient in terms of h then. Well, again, so then part B says, what do you deduce about the gradient of the tangent at the point 416, right? So again, if we have the curve x squared, let's say my point 416 is here, right? That's the point G, right? So what's happening is we're basically measuring the gradient of the tangent of the curve at that point, right? Something roughly like that, right? So what's the gradient of the tangent? Well, what we're doing is effectively we're taking points P on the curve and we're moving them closer and closer to G. And then eventually the gradient between G and P will match the gradient of the tangent to get a gradient for the curve at the point. So the gradient of the tangent at the point G then, right? Well, what do we notice again? The gradients are starting to go towards 8, right? So I think the gradient of the tangent at G is going to be 8, right? And that makes sense because remember the h, right? If h basically goes to 0, because basically h is the gap between my points G and this point P, but P is moving closer and closer to G, which means if P is basically right next to G, there's no gap between them. So this gap H is basically 0, because again, remember the H here, I'm starting at P is 5, so that means the gap is going to be 1 between 5 and when G is 4 for X. Here, then it's 4.5, so the gap is now 0.5. And then here in part 3, we're now at 4.1, so it's getting closer to 4, right? So that means H is 0.1, and then here, H will be 0.01. So H is getting closer and closer to 0, meaning the gap, or the distance between G and P, is diminishing. So we're getting closer and closer to the point G. And so basically, when it's basically there's no gap between them, we get 0, so we get 8 there. So that would be my gradient then, okay? So the gradient of the tangent to the curve at G, remember the curve is x squared at G, is 8, okay? Via this sort of method, right? Okay. And okay, well, again, so this idea are basically going towards a point to find a gradient of the tangent. We will be using in the next section. So hopefully this idea sort of made sense, how we get closer and closer towards a point, which allows me to get a closer and closer approximation for the gradient. Okay. Right, we're going to finish off with an exam question then. There's not a lot to this section, but as I said, it's important as a foundation for later content. So we're given this curve again 3x squared minus 2, very similar. So again, I have the point P is 210 here, and I have a point Q. So again, the idea is Q is going to end up being towards my point P, right? So Q would then, if we keep moving Q closer to P, then the gradient between Q and P, right, is going to sort of match the gradient of the tangent at P. Anyway, so the Q has x coordinate 2 plus h. So P has coordinate 210, and Q, we're told, has an x coordinate of h plus 2, right? And it also lies on the curve. But obviously then it's going to have a y coordinate, right? And it says find a gradient of the line PQ. So again, the gradient is going to be changing y over changing x. But my problem here is I don't have an actual expression for the y coordinate of Q at the moment. How do I find that then? So then, well, remember, Q is simply on the curve. Remember, the curve is y is 3x squared minus 2, right? Well, if I know x is this expression h plus 2, can't I substitute that into here to get my y coordinate, right? If I do that then, so then that means y would be 3 lots of h plus 2 all squared for x minus 2. Then I just need to expand and simplify, right? So that'd be 3 lots of, if I expand h plus 2 squared, that'd be h squared add 2h add 2h be 4h plus 4, and then all minus 2. If I then expand this out, I get 3h squared add 4 times 3 is 12h. Add 12, take away 2. Then lastly, 3h squared add 12h, then 12 take away 2 is plus 10. And so there we are. So therefore, finally, my point P is 210, and my point Q, in terms of H, is H plus 2, and then Y is this quadratic, 3H squared add 12H plus 10, okay? Now then, my gradient then between P and Q, in this case, is going to be, again, if we do change in Y, change in X, so again, Q, the Y is this whole expression here, 3h squared add 12h plus 10, take away 10, right, at P, over changing x then, so at Q, x is h plus 2, take away 2 from P. So then we can sort of simplify some stuff, right? Well, I notice 10 minus 10 cancel at the top, So 3h squared are 12h. And likewise, 2 minus 2 cancels as well to be left with h. And then I can simplify it, right? Because again, the same idea, I can factorise the h out. So I can also factor a 3 out as well, actually. So get 3h on the top of h, add 4 divided by h. And so this would equal then 3 lots of, because the h will cancel out, 3 lots of h plus 4. Then if we expand it, we get 3h add 12. Cool. So then that is my simplified gradient of PQ, right? So the gradient from P to Q in terms of h. Right, so that's the question then. But again, the theory, the idea behind this then is basically as sort of the gap then between Q and P. So here Q, let's say Q is, I don't know what Q is, but let's say we're basically moving Q closer and closer to P, right? That gap then, right? So imagine the gap here, that gap H from P to Q is shortening, right? We're getting closer and closer to P, meaning the gap, right, between P and Q, the H, right, is getting closer to 0. And so as we've seen, as we get closer to 0, as the 2 points basically come together, the gradient between those 2 points is basically matching the gradient we know from the tangent at the point, right? So the gradient between the 2 points when they get closer is the accurate gradient at that point of the curve, right? And so therefore then, this gap H then, indeed, when it basically goes to 0 then, again as we've seen, when the 2 points basically are next to each other, we're just left with 12. And so then, quite reasonably, you'd say that therefore the gradient at the point Q on the curve, the gradient at the point Q, point P, would be 12, right, in the long run, right? Eventually Q would be next to P, and so that'll tell us the gradient would be 12, okay? And you would be right in saying that. So we will be looking at this idea of 2 points being close to each other to then find the gradient in this way. We will be looking at this more formally in the next section. But for now, just hopefully you got the idea that we can that the tangent, right, the gradient of the tangent at a point on the curve, right, gives us the actual gradient of the curve at that point, right? So if we draw a little tangent at P, let's say there, right, so the point of the grade, a very rough gradient, but if we draw a gradient line at the point P which touches the curve at the point, that gradient will tell us the gradient of the curve, so the steepness of the curve at the point P. Okay, right, so that's it for now, but I'll see you next time.